Our goal is to describe rotational interactions in dynamics, things like forces, energies, work, and how they apply to rotational motion. From our perspective on angular acceleration and velocity, we can describe a motion that's given, but we don't necessarily know how forces are going to affect that motion just yet. Before we can do that, we need to introduce an important property for a rotating object that plays a role similar to the mass of a moving object, and that quantity is called its moment of inertia. Let's see how the moment of inertia comes about by considering the kinetic energy of a rotating object. We consider kinetic energy because it's a quantity that just adds up. If there are more pieces of mass moving, then each one contributes its own kinetic energy to the total. For an object rotating at angular velocity omega, let's look at a piece with a mass m and a position vector r. It's important that the position r be measured from the axis of rotation, because that's what determines how quickly that bit of mass is moving. If we just wrote down the kinetic energy of this piece of mass, then it would be 1/2 mv squared. Let's label this as kinetic energy of mass I. A real rotating object, though, has a lot of different chunks of mass all dispersed throughout it. So its total kinetic energy, due to that rotational motion alone, should be a sum of the kinetic energy of all of the little chunks. So a sum over the index I can take on some large value just to count all the chunks in the object. So this works fine if our object is divisible into small pieces. But if the object is truly continuous, maybe it's just a solid block of metal here, then the chunks of mass mi can be made artificially small. And we can convert our summation here into an integral. Our small bit of integration is the mass. And we have our factor of 1/2 and our factor of v squared. Now this doesn't really, these wouldn't have indices anymore. We would have a v as a function of position, and the dm would have a function of position as well. So this doesn't really help us to do this integral, though. It's still quite difficult. We have to have a way of expressing where all the mass is. But one thing that can help us is, in a rigid motion, the velocity of a given chunk of mass is dependent on its distance from the axis, its angular velocity of the rotation, and it points in the theta hat direction, tangential to the circle. So v squared is equal to omega squared r squared. So we get a small simplification if we consider calculating the kinetic energy. We get 1/2 times an integral that I'll still be writing just formally as dm but the angular velocity for each bit of mass is the same. So that can be considered apart from this integral or this sum. So the thing that appears in the integral is still not something we can just do, but it's important to realize what it depends on here. It depends on where the bits of mass are and how far the bits of mass are away from the axis of rotation. So this quantity in brackets here, even though it might be difficult or take some work to calculate, we can be sure that this quantity depends on the size, the shape, and the distribution of mass in the object, and not on its current state of motion. This quantity in brackets here, therefore, is a special property of just that object on its own, whether it's moving or not. And we call that the moment of inertia. The symbol for it is a capital I, and the formal definition is the integral of r squared for all the bits of mass in the object. Now, to get a feeling for what this integral entails, let's do what's instructed for a simple object. Let's consider a one-dimensional object, a rod or a bar, and this bar has a uniform density of matter in it, so the distribution is even, and we'll use the variable capital L to refer to its total length, and we'll place the axis at the center of the rod, so L over 2. Right, so this distance is L over 2. All right, so the rod has a total mass, and we'll symbolize that total mass by a capital M. And the total mass will be related to the density of the rod and its length. So we'll use a density factor of lambda. That will be our symbol for mass per unit length. And the mass per unit length times the total length of the rod will be the total mass. If you're raising your eyebrow at the use of this new symbol lambda, you can consider this to be the actual density of the material in kilograms per cubic meter, multiplied by the cross-sectional area of the rod. So the amount of mass that would be in a thin slice of width dl. So with this mass per unit length declared, then we can set up our moment of inertia integral. So we'll use the coordinate x to go from the left side of the rod at x equals 0 to the far right corner of the rod at x equals to L. So our limits of integration are from 0 to L. And we're going to be integrating over x, not m. So to match up with the definition here, and we want to integrate over x, what we will have to do is, basically we're doing a change of integration variable, so we have dm over dx multiplied by dx, and that's how we get our dm. Then our value of r is going to be x minus L over 2. That's the distance from the axis. And that gets squared. Now our variable here, dm dx, is the mass per distance along the rod. So this is simply the linear mass density. All right, so let's do this integral. The first thing I'm going to do is move this constant lambda out to the front. The second thing I'm going to do is expand this square. So x squared minus 2 times L over 2 times x, so I'll have minus Lx, and then plus L squared over 4. So that's expanding the square, and then I'll come up to this location and do the power rule on these terms to integrate them. So it would be lambda, then we'll have x cubed over 3 minus L x squared over 2 plus L squared over 4 times x. And this will be evaluated at x equals L and x equals 0, and we'll take the difference of those. So doing that, we will get, basically, we have an x in every term, so we'll have L cubed over 3 minus L times L squared, so again an L cubed over 2, and then L squared times L, so again an L cubed over 4. Subtracting the values at 0, if we plug in x equals 0, these terms are all 0. Okay, so there's a little bit of fractions here to add up. What does this come out to? Well, I think it's going to be easiest to look at the second two. This is negative 1/2 and positive 1/4. So that adds to negative 1/4. And then we would have 1/3 minus 1/4. And if you want to get a common denominator there, it is 12, right? So it's 4/12 minus 3/12. So we'll get lambda L cubed over 12. So here is a formula for the moment of inertia of that rod that is correct. Lambda L cubed over 12. Now when we write out moments of inertia, it's conventional not to list them in terms of the density, but in terms of the total size and the total mass of the object. So before we put a box around this, we're going to use the fact that lambda times L is equal to m. So we have m L squared over 12. And that is the moment of inertia of this rod to rotate about its center. Now notice that the moment of inertia is not simply the same as the mass. A moment of inertia would be larger if the mass of the object is larger. They're in direct proportion. But it also depends on the size of the object. If this rod were to maintain the same mass, but somehow grow in length, the moment of inertia would get larger. Just because to move that mass, we need to make the ends of the rod move faster if it's got a longer length. So more mass is moving and it has more inertia. Let's now try to summarize what we've done here. We kind of approached this in an ad hoc manner, but how can we calculate the moment of inertia for more shapes? Get a general plan for doing that. Let's summarize what we did. So the first step was to define the size, shape of the object. And we do this by choosing coordinates. And limits for those coordinates to run over. So in our example with the rod, we said x will describe the distance along the rod, and it will be 0 at the left, and it will go up to L at the right. The second thing we need to do is take care of this dm in the definition. We need to actually, we never do it in terms of m's, we need to relate dm to small chunks of what's basically volume, area, or length on the object. So we relate dm to dx dx dy for area, or dx dy dz for volume, with the appropriate density. So what this would look like is, in terms of length, dm is equal to a linear mass density times a small width in position. In terms of areas, if the object is a flat planar object, we can write dm as a surface density times a small chunk of area, dx dy. All right, so lambda is linear mass density, sigma is areal mass density. And if we have a three-dimensional object, then we use the volume mass density rho, kilograms per cubic meter. So that is our second step. Our third step was then to take care of the r squared in the integral, right? Use our coordinates that we defined in step 1 to express r, which is the distance from the axis. And in this step, it becomes clear that the location of the axis makes a difference. If our coordinates are far from the axis, r will be large, and if they're close to the axis, r will be small. And the final step is to do the integrals. Now, these integrals are usually not difficult to do. They're not going to involve crazy functions like trig functions or logarithms or anything like that, because most objects, turns out most materials, they do have usually constant mass densities. Constant linear mass densities, constant mass densities. You can even look these up in tables for various metals and materials. So the density is going to be usually a constant that can be taken outside of the integral. So that's kind of easy. The dependence on the coordinates also turns out to be usually rather tame. We have r squared here, which is just going to generally take our x, y, or z, or our angles and our distances, and raise them to some power. So we're going to be doing integrals that involve a lot of power laws, maybe some trig functions if we're using polar coordinates, but generally pretty tame integrands. The real hard part of these integrals is usually then working with the limits, choosing the right limits, way back on step 1. So let's test out this procedure, and we'll go through it for a somewhat of a specific shape. Okay, I'm going to do the moment of inertia of what's called an annulus. It's a two-dimensional ring. It's got an outer radius, so it's like a disk, but it's got a hole in the middle of radius a, so it's empty in the middle. So it's like like a washer or a wheel or something like that. And within the region between A and B, we'll say that there's a constant area mass density. The total area of this object is just the area of the outer circle, pi b squared, minus the area of the inner circle, pi a squared. So that means that the mass density, sigma, is equal to the total mass over this area value. It's good to keep that in mind. So we've set up our size and our shape. It's determined by A and B. And now we need to choose coordinates and limits. So how do we select out a specific location on this annulus? we're going to do so, since it has a rotational circular symmetry, we're going to do this in polar coordinates. So we're going to let r be the coordinate from the center to some point. So we'll be working with r values that go from A to B. So from inner radius to outer radius, that's the only place we've got mass. And we'll let theta describe the angle in this coordinate system that locates the bit of mass in the annulus. So that's step one. The angle will be able to go between 0 and 2 pi. Now step two, I have to relate a small bit of mass to these coordinates. So my dm will be, I'm in a two-dimensional case, so I'll be a sigma. I don't have x and y here. Instead, I have r and theta. So what I need is a way to describe a small element of volume on this circle with these two coordinates. So if I look at a small element of volume here, this square, its width is equal to dr, and its height is equal to r d theta. So a given angle difference produces a larger width at a farther radius away. So my area element here is r dr d theta. This might seem familiar to you if you've done some two-dimensional integrations in your calculus studies. So now I've related my dm to my surface area element, basically. So step two is finished. Now step three, use my coordinates that I've chosen to express r, the distance from the axis. This step is particularly simple for this shape. I already chose r to be the distance from the center, and if the axis is at the center, then I don't really have to do any work here. R for the distance from the axis is just the same as r as my coordinate. So then I'm on step four, the last step, to do the integrals. So I'm integrating sigma r dr d theta. Theta is the outside variable that's going from 0 to 2 pi. R is the inside variable that's going from A to B. So that's my integral symbol, my dm, and my r squared is just that, r squared. Okay? So my claim before about these integrals not being usually too nasty was seems to be correct here. The sigma is a constant. The integral over the angles, the d theta from 0 to 2 pi, there's no theta dependence in any of these, so it's just 2 pi. And the integral of r is, so we've got an r squared, and a dr. So that's going to be r cubed dr. So my antiderivative will be r to the fourth. Now I do have to take this at the upper limit b minus at the lower limit a, so I'll get b to the fourth over 4 minus a to the fourth over 4. So this expression here is a correct way to get the moment of inertia of this annulus. 2 pi times the mass density times the difference of the inner and outer radius taken to the fourth power divided by 4. But as I said when we did the rod, it's convention to express this in terms of the total mass. Why? Well, generally it's easier to just take your object and toss on a scale than it is to guess what it's made of and look up its density or volume. So let's try to express this in terms of the mass. We'll take our sigma and plug it in here. So I will be equal to 2 pi times sigma. which is the mass, divided by total area, pi b squared minus pi a squared, multiplied by this factor in the parentheses. So that's also a correct formula, but it could be slightly simpler. There's a pi here and a pi on both terms in the denominator. So that pi can be canceled. There's a 2 here and a 4 in both terms there. So that 4 can be canceled. And there's actually another kind of tricky cancellation that could go on here. In this, I miswrote this one. That was a to the 4th power. In the numerator here, we have b to the 4th minus a to the 4th. And in the denominator, we have b squared minus a squared. Now, when you have the difference of two squares, that can always be written as the sum of the two values times their difference. So this b fourth minus a fourth can be interpreted as b squared minus a squared multiplied by the quantity b squared plus a squared. So these two numerators and denominators here with the b's and the a's can actually cancel somewhat. So we'll cancel out this pi. We'll cancel out these 2's and 4's to make a 2 on the bottom. And then we'll be able to cancel out the b fourth and the a fourth down to a squared. So it will be a squared plus b squared. And that's just about as simple as we can get it. It clearly exhibits this form of some mass times some length scales squared divided by some, or multiplied by some fraction. Here the fraction is 1/2. Okay. Now that we know how to do that and what it means, I'll inform you that generally engineers don't go around recalculating the moment of inertia of various shapes all the time. As you see for this problem here with the annulus, once we've got this formula, we know how to get it for any donut shape. It doesn't really need to be gone through over and over and over. It's still good to know where it comes from, but in practice, we would usually turn to a table of formulas and say, what's my shape and what's the formula? So I'm going to put up a slide here that shows you some various common formulas to calculate moment of inertias. That table is great if you have exactly one of those shapes, say a sphere. But what do you do if you've got maybe something a little more complicated, like two spheres on the end of a rod? Well, in those cases, we have a way to use the values in the table and combine them together to get the moment of inertia of a more complicated object without having to turn all the way back to a fundamental integral. This way of combining moments of inertia to get the total for a complicated object is called the parallel axis theorem. What does the parallel axis theorem say? It says that if we have a shape that we know about, but it's rotating around an axis that's different from the one specified in the table, then we can find the moment of inertia of that object rotating around a different axis, an axis parallel to its natural axis, by adding the moment of inertia about this center of mass axis to the product of the total mass times the distance between the center of mass axis and the actual axis it's rotating about squared. So we have two terms here. One that is intrinsically related to the shape and size of the object, and the second which is related to how far it is from the axis of actual rotation. So that gives us a way to get the moment of inertia of all the various pieces of a rotating object. Say we had something like the barbell, with a sphere on each end and a rod joining them in the middle, and that whole object being rotated around an axis that was through the center of the rod. So if each sphere had a mass of m1 and a radius of r1, and the rod had a mass of m2 and a length of L2, then what would our moment of inertia be? We have three pieces to this object, so we can find the moment of inertia of each one and add them all together. Let's do it for the rod first. From the rod, we have a contribution that's exactly equal to 1/2 m2 times L2, or 1/12 m2 L2 squared. We did this calculation for the rod. Then for the sphere, we would add the moment of inertia about its center. If we look at the table, for a solid sphere, that's 2/5 m1 r1 squared. Both spheres have a radius of r1. That is the moment of inertia of the sphere around its center of mass. To get the total moment of inertia that the sphere contributes when it's rotated around this axis, we still have to add on the mass of the sphere times its distance from the center. Now be careful, the distance to the center is not L2. It is half of L2 plus the radius of the sphere. So we have L2 over 2 plus R1 squared. That is the distance between the center of mass of the object, the sphere, and the axis of rotation. So this is the contribution of one of the spheres. The contribution of the other sphere will actually be identical to that. So we can just multiply that by 2. And this is the formula for the moment of inertia of this complicated object. It's definitely more complicated of a formula, but nothing we can't handle plugging into.